Hello, everyone, and thank you for listening to the Fabrication Friday podcast. I'm your host, Joe Fairley, certified prosthetist, 3D printing enthusiast, and owner of Ascent Fabrication. Fabrication Friday is an all-around fun time where I talk about 3D printing applications, conduct interviews with industry leaders, and much more. Come join us every Friday for an informational discussion around the evolution of the additive manufacturing field and how we utilize various digital workflows and 3D printing methods in our daily work at Ascent Fabrication. Hello, everyone, and welcome to the Fabrication Friday podcast. I'm your host, Joe Fairley, certified prosthetist, owner of Ascent Fabrication, and of course, 3D printing enthusiast. So this week, we are going to get right into the print of the week. The print of the week was pretty interesting. So I am building a ladder shelf for my home use. My wife and I had actually gone to the store, got the wood that we wanted, did some sanding, did some staining, and then did some lacquering with an acrylic finish, and measured out exactly how we wanted the shelf to be laid out. Really like that kind of wood finish, but we're actually soon looking into 3D printing these ladder shelves with the black belt 3D printer. So getting a little bit more off topic, we'll get into the black belt 3D printer at another time with some different use cases. But for this ladder shelf, my wife and I wanted to, put this together ourselves and make it our own. And I wanted some brackets to actually hold together, those pieces of wood together, rather than source them, at the hardware store or, somewhere else online. I decided to design and print them because why not? We have these materials and machines readily available, just to show off exactly what can be designed, what can be printed. Have to give some kudos to Slant 3D, Gabe Bentz there. He actually posted a video earlier on this week through his YouTube page. Definitely go give it a look on exactly how to design these type of brackets for high scale production 3D printing. So Slant 3D has a huge 3D print farm out in Boise, Idaho. They really know what they're doing over there, guys. Go check them out. Looking into that kind of high scale production status that CentFab is getting into here on the East Coast, but they've got a nice operation going on over there on the almost the West Coast. So looking at the bracket design here, trying to take into account some design for additive manufacturing techniques. That's going to be the theme of this whole podcast here this week is DfAM, design for additive manufacturing. So in order to design a part that you want to be robust and have the easiest time printing, least amount of support structures, least amount of post-processing, we want to design this bracket in a certain way that's going to optimize that print time. Again, less post-processing, the better, and making sure the print quality actually comes out okay and the part functions the way that we want it to. So the bracket here was printed, in this kind of triangular, not cuboidal shape, but kind of full shape instead of a shelled out shape, in order to print it well for additive manufacturing, having to print infill patterns, having some of the hole structures countersunk so that we can get the screw into place. This print is going to print out actually in groups of 12. That kind of optimized the amount of print time that I wanted and the number that I could fit on the build volume of the artillery Sidewinder X2. It's going to be printed out of just black PLA. This is going to be way more durable than it really needs to be, even still in PLA. I think I did about 15% honeycomb infill for this and 2 walls, 2 perimeters. We're looking at, for the 20 of these that I actually need, about 550 grams of PLA with a print time of about 28 hours. We could probably push the print time a little bit further on that, But with some of the print times that we're looking at between 30, 40 millimeters per second, that's kind of the print time that, is perfectly fine for this use case. We're looking to get these out within 1 day anyways, for 20 of them for one single shelf, doing on one printer on 2 different builds. The first build of 12 takes about 17 hours. So the next build of 8, we can then expect to take, maybe around 13, 14 hours, trying to get that print time down to where you're actually able to swap that print over in 1 day, so that you can have that next print going, and still keep that kind of 24-hour period of turnaround time. People kind of balk at some, print times thinking, 28 hours for printing. Still 1 day. I mean, how much printing can you really get done in 1 day? How much regular manufacturing can you get done in 1 day? For parts like these, that is going to end up costing me 550 grams of PLA, filament. We're looking at, under $25, definitely under $25, sorry, under like $13 worth of filament. So looking at that print time, that turnaround time of about a day, looking at about $13 worth of material, in just, nice solid black PLA. It's going to be kind of hidden underneath the shelves. So you're really not going to see it very much. Not super concerned about surface quality, but the print's coming out just fine. We're printing with a 0.6 millimeter nozzle. So again, print time versus kind of how we design this part is really going to dictate that overall print time and how quickly we can print something and how reliably it'll print. So getting into the kind of theme again of the podcast today, and it's actually our tech tip of the week, is this idea of design for additive manufacturing. So when we talk about how we go about a process of either starting with a 3D scan, whether we're in prosthetics and orthotics and we're working with patients, or we're starting out with an idea for a part, that could constitute the need for measurements or maybe a sketch of, what we're actually wanting to recreate if it's reverse engineering. So whether we're starting out with either of those 2 items, you have to constantly be thinking about, okay, how do I want this part to actually come out? Will its geometry constrain me from printing it well? So taking a look at some of the, geometrical constraints of 3D printing through FDM 3D printing, I should say, again, designed for additive manufacturing, whether you're 3D printing metal, whether you're 3D printing through powder bed fusion or FDM, SLA, resin printing, there are going to be different considerations for your part design, based off of that actual, printing process that you're using. We don't have the same requirements for powder bed fusion that we do for FDM 3D printing, for instance. So for powder bed fusion, the entire build cake constitutes the actual support material that's used during the print. So we can have these very intricate structures that are printed within this bed of powder, versus a FDM, spooled filament layer by layer print, where if we're starting to print over, actual overhangs, where we're printing over air, if you're 45 degrees or less than that for an overhang angle, you're definitely going to need some kind of support structure. It's very unlikely that you're going to be able to get away with no support structure when you're using one of the typical setups for 3D printing on FDM, unless you're printing with a belt printer. Hint, hint, the black belt again. Printing with a black belt, you print actually at a 45, 35, 25 degree angle, I think maybe even down to 15 degrees, where you can have a lot less support structures because you're actually building on at that angle, which is pretty interesting. You're not building straight down from the XY axis. You're actually building it just at a slight angle. So think about the the way that you actually want to print your part. And if your part is not actually constrained by the part cost, then you might be able to get away with, a little bit more intricate design with having more powder bed fusion. Whether we are talking about, trying to go for FDM 3D printing and using prototyping processes with FDM, and then maybe moving to a powder bed fusion like multi-jet fusion from HP, or selective laser sintering through EOS, Formlabs, or Farsoon, a couple different SLS 3D printer companies. Just basically thinking about what is the end product going to be, and what does my cost of that part have to be in order for it to be worth it for me to print this thing. So with those cost ideas in mind, now we look at the intricacies of, okay, let's say we're setting up a part for FDM 3D printing. With design for additive manufacturing techniques in mind, first off, the thing that I think about is our wall thickness. How thick do we actually have to print that part? And how many perimeters, how many times am I going to go around the perimeter of that part to create a nice surface finish, as well as to create some structural integrity? So typically we start off with at least 2 perimeters for surface finish quality purposes, increasing it from there depending on the level of real structure integrity that we need. That is also going to be dependent on our nozzle width. So the nozzle width being 0.4, 0.6, 1 millimeter, 1.2, going up to 2.5, and even larger with some high-end, high flow machines like Filament Innovations. We can actually get away with more wall perimeters if we go with a smaller nozzle, or just one single wall thickness, and we get into vase mode 3D printing through this FDM process, where we just have one continuous perimeter extruded. And again, then that complicates things through vase mode 3D printing, where we're going to have to constrain our part even further in how we design it. Through vase mode 3D printing, we are printing just the outer perimeter of that part. So when we have to have some different components and other structures that are adding onto a prosthetic socket, we do a lot of vase mode 3D printing in prosthetics, and orthotics for that matter, for ankle foot orthoses or something like that. You're going to want to think about how you're actually designing that part within whichever software you're using, Mesh Mixer, Fusion 360, what have you. And, seeing how that part is actually going to be integrated within, another part, say the socket in prosthetics, so that once you go to the slicer, don't forget the slicer. Now, the slicer is absolutely a huge key feature, of this design for additive manufacturing. Once you put that part in the slicer, is the slicer going to react exactly how you think it's going to react? So, looking at the application for your device is going to limit how you set this part up for successful 3D printing. Say we aren't printing in vase mode and we're printing multiple perimeters, and say I want a uniform wall thickness of 3 millimeters. Well, I'm going to end up doing maybe a 1 millimeter nozzle and 3 perimeters to go around and make me up that 3 millimeter thickness. That's going to be perfectly fine, even if you do have some overlap percentage with those perimeters. You're going to end up having about a 3 millimeter wall thickness. Now, infill, when we're talking about infill, infill percentage and different infill patterns can have drastically different, applications on the same part. So you have to think about infill also as sort of a support material, depending on how you're printing your part. If it's a overall closed part, or maybe it's an open part, closed meaning like looking at the shelf bracket right here that we were looking at, you see that it has, a top surface to that print. Well, if I don't have enough infill percentage or the right pattern, then you might not be able to actually close off that top. Because if you do a number of top and bottom solid layers and you want a closed part, then the top solid layers are just going to droop into the part again. So increasing your infill percentage based off of, again, how you want that surface finish to look and function like is going to be pretty crucial. So, having an actual wall thickness or perimeters to dictate kind of your mostly uniform thickness of the part, and then taking into account those top and bottom solid layers, those will also should be, again, the kind of exact number of perimeters, the same wall thickness that you're going to want throughout the part. So, if you increase the number of top solid layers, bottom solid layers, then you're going to have a thicker part of that design. So, just because you design a part in Fusion 360, once you go to the slicer program like Prusa Slicer, Ultimaker's Cura, what have you, Simplify 3D, you might be actually changing the design of the part, but just by slicing it. And sometimes that can actually be a bet to your benefit if you want to get creative with how you're going to, print that final part. So infill percentage, infill pattern is going to play a role in that structural integrity of the part, or could also play a role into maybe the cushioning feature of a part. We love to print with ColorFab's VarioSure, our Foam Flex Air flexible inner sockets for the prosthetic market. Integrate these cushions in between the outside and inside walls, where we're using an infill pattern, gyroid infill pattern at a certain percentage to actually create that cushioning within the walls of that device. So this could have other applications within custom seating, or really any other type of cushioning. You could have a bike seat be very cushioned. You could have a headrest in a car be very cushioned, or something else in your car, another cushion in your car. Maybe we get into some cushioning for these 3D printed homes that are coming out, and you have some 3D printed furniture where we have this custom design couch with this cushions, printing out of VarioSure. It could happen. Wink, wink, nudge, nudge. We'll see what happens down the line here for us. Just throwing that out there. But again, there's a lot of ways that you can manipulate your part inner structure to get a different result for how you want your part to function. So looking at that infill percentage, infill pattern, number of walls that you're putting into the part, walls, perimeters, looking at the top and bottom solid layers for achieving a nice surface finish, and then really print orientation. Okay, so print orientation, for instance, the shelf bracket here, again, we're printing this on its really thinnest side that we could, while we don't have really any overhang angles that we have to worry about putting any support structure in. We have about a 55-degree angle from the print bed off of the main body of the part. So about 55 is kind of that, sweet spot of that's about as far as we want to go before we start, needing support material past that. So if I oriented this part any other way, I would actually have overhang, structures because of these holes that are integrated within the part, to a point where it wouldn't be really feasible for me to print it in any other orientation without having to worry about that part, not coming out the way that I want it to. And thinking about some of Slant 3D's suggestions for, how do we scale the level of production of a part like this? If we're trying to print out hundreds or thousands or hundreds of thousands of these units, what's going to be the easiest way to print it with the least amount of post-processing and the easiest way to get it off of the print bed too. So went over a little bit about print orientation, different slicer settings that you can play around with to alter the features of your part. I would suggest that when you're actually designing your part, keep it true to your thicknesses in your design. So any wall thicknesses that you have, any distances, maybe you need to take into account some level of shrinkage of the material. If it's polypropylene or a different material that shrinks as it cools, you might have a little bit of a tolerance to adjust to according to how your part is being printed and at what resolution. The layer height and resolution is absolutely going to affect the integrity of your part as well. So having a 0.4 millimeter layer height versus a 1 millimeter layer height versus something bigger, you want to make sure that those layers are actually going to be sort of squished together, and so the material actually bonds how it's supposed to, in order to create that strongest part that you're looking for. Typically, we start out with a layer height that is about half the nozzle width as a good starting point. If we want to be able to squish that layer maybe just a little bit more, maybe we go 0.1 millimeters beneath that halfway point. Otherwise, again, depending on the print time that you're looking for, increase the layer height. And if you're looking for aesthetics, the layering can actually be a nice aesthetically pleasing feature in a part. Maybe you increase the layer height to get something that is, better suited to portray light. Maybe you're printing a light shade or part of a light fixture to dance around light in a cool way with a shiny filament or a see-through PETG filament or something like that. So taking into account the actual characteristics of the materials that you're using as well, how they flow, how well the layers bond together, how quickly do you need to print that part in order for the layer, when it comes back around to that same point, to actually bond well at whatever temperatures you're going to be printing at. So cooling percentages, obviously cooling and heating are going to be other indicative characteristics of the materials itself. You can only print really as fast as you can cool down a part, otherwise you run into warping issues. And just maybe you actually don't need any cooling depending on the materials. We've talked about not cooling TPU in some instances because it cools very quickly just on its own. So a lot of different considerations there based around how we're going to design our part, and then how we're going to slice our part, and how we're actually going to print it. Then thinking about any post-processing that we need to do we need to plan ahead for that as well? Maybe we're not using the auto-generated support structures within a slicer. Maybe we're actually designing our own support structures within a part that's easily going to be able to break off or just be less waste material at the end of the print. So, thinking about the ways that you're going to support your part during a print could be pretty useful if you want to create your own support structures. I would say the newer support structures that some slicers are coming out with, tree supports, while they look pretty cool, only in some instances do they work. If you have a really large flat surface that you're trying to bridge over for support, then you're not going to be able to use tree supports. You'd have to use something like honeycomb or rectilinear support structure like that. That's going to bridge the entire way. So looking at, again, design for additive manufacturing, what does that mean? It means you're taking into account the materials that you're using, the printer that you're using, the design constraints for what your end part needs to be, and then looking at what's going to be the easiest way and the cheapest way to print that part. Really taking into account too, the how that product is going to look when it's finished, right? So if you need to tweak some settings in order to get a part to actually look nice at the very end, you might have some under extrusion where you're having little blobs of plastic that are basically missing from the part. Maybe you have to actually dry out your filament. Maybe you are evaporating some water within the filament while you're printing, and that's assisting the under extrusion. It's adding to that under extrusion that's happening. So drying out your filament, taking care of your printers as well, making sure there's no clogs in your nozzle, actually cleaning out your nozzle from time to time or replacing your nozzle, making sure you get that perfect print, is going to be really, really key to having that print be consistent and reliable every time. So one of the other things that we do here at Ascent Fab, we've talked a little bit about in the past, but we go out and do trainings for people. So we will come out to any site for a couple days where these people have a printer that we will support, and looking at the actual application for what they want to print. We will take them from step A to Z of either 3D scanning something or going through a reverse engineering process to actually come up with that end part that they're looking for. In some cases too, we can test print your part first before trying to print it on your own. And in that case, we're trying to print it on our printers here in Ascent Fabrication, and then we end up having those print settings that we know work that we can send you to print as well. So like for instance, last week I went out to Buffalo for a training with a clinic in prosthetics and orthotics, and we used the Artillery Sidewinder X2 with Mesh Mixer as our design software, Comb Scan as our 3D scanning software, and Prusa Slicer as our free slicing program. So looking at that workflow, we were able to take a couple scans of a couple patients, and they're pretty focused on the pediatric lower extremity and lower extremity orthotics, scoliosis, cranial helmets, and we wanted to start to print out some of those devices. So went out there for 2 days, showed them start to finish how to go from that 3D scan of a patient to a product that they could successfully and be proud of putting on a patient and fitting it, and having a lot of different benefits for the patient, where we added cushioning into the inner boot structure that was a soft material, Variosure color fab, having those cushions in the malleoli, for extra cushioning around the bony anatomy, and then a polypropylene AFO lightweight, cool colors for the kiddos. We can imprint some designs on that too. So just taking them step by step through that process. This week, I get to go out to Massachusetts to do the same thing. Another group out there in prosthetics and orthotics, and we get to go through the same thing with the Artillery Sidewinder, as well as the Filament Innovations Icarus. Again, we run the full gambit of the low end 3D printers up to the more industrial 3D printing. So no matter what your application, we're really looking to figure out how to print different things. If we haven't printed something before, we're always going to use these design for additive manufacturing techniques to come up with a way to actually print it and print it successfully. Maybe we have to go through a couple different materials to find the right material. Maybe we have to go through a couple design iterations of a prototype. But getting to that end result is really, that step-by-step process of figuring out how we're going to design it, how we're going to slice it, how it's going to print, how it's going to get post-processed. So thinking about that entire process all the way through is really what we want to focus on when we're thinking about trying to 3D print something with a specific material for a specific process, and looking towards what outcome we're looking for. So, if you're looking for training in that industry in prosthetics and orthotics, or another industry as well, we have these reverse engineering techniques very fine-tuned here at Ascent Fab. So definitely, look into what we could offer for training. Aside from that, we're trying to create some fun stuff going on here in Saratoga Springs, New York. We're going to create more of a community outreach here, where I'd like to start an open print night where people can come in and actually use the 3D printers, sort of in like a maker space kind of way, but with a lot of very hands-on focused, only 3D printing and design for additive manufacturing instruction right here on site in upstate New York. So people could come in, they can use the 3D printers that we have available at that time, and some of the different materials that we have to use. Don't forget that we also sell a lot of the materials we use as well. So if you're looking for quality materials, people who know how to use them, that's kind of what we're looking to put out there, and just help promote, additive manufacturing and 3D printing applications for different industries. I've been pretty interested lately in getting into 3D printing some furniture, and a couple other things that I have some cool ideas on. So this black belt printer, printing completely continuously and really almost infinitely as long as we want, that's going to open up some doors to 3D printing things that couldn't otherwise be 3D printed. We're looking at printing like the size of a 2x4 by 10 feet, that kind of scale. Or if we're printing parts over and over again in succession, like I want to print these 20 shelf brackets, I could set that up on the black belt, and with its dual extrusion, we could have 10 of those printed, probably in a faster fashion than the 20 that are printing right now on the artillery sidewinder. And they can pop right off the end of the bed when they're done. And then we can keep on printing that same material for a different device right after that in succession. You can have kind of a print queue going on, so you can upload different things and move them around based off of where you want them on the bed, but also where you want them in the queue. So that's going to be really cool and interesting. We're getting our black belt here within the next couple weeks, and really interested to find a lot of very practical applications for this type of 3D printing. We're printing a lot of things that are very more in the household kind of space now. So I printed myself a floating shelf. That's going to become one of our products, in different lengths and different sizes, different colors, couple different materials maybe. And we had a ladder, the shelf idea here that we're going to start printing as well in the black belt, printing all those parts. And so the shelf, we just printed ourselves a garbage can the other day. We're going to print ourselves a recycling bin, because I said, okay, well, people are putting some recycled things into the garbage bin. Why are we doing that? Come on, we're looking at saving materials, not tossing something that could be recyclable in the garbage. So we're going to print a recycle bin too now. Guess we actually have to do that. So we've got a recycle bin that prints out in just like 2 hours. 2-3 hours, something like that, in vase mode. And practical applications for 3D printing. There's so many different applications for printing that really we haven't even touched on yet. There are some companies that I know about that are kind of keeping some things behind secret doors, and a lot of different products definitely will be coming out in the coming years. that you might not even know is actually 3D printed. There are some stuff that's out there printed already. I'm 99% sure, but the top on my Yeti thermos for coffee thermos, I'm 99% sure that is 3D printed MJF vapor smoothed. Haven't reached out to Yeti to ask them, but it looks exactly like an MJF part that I've seen before, and doesn't specifically look injection molded. So there might already be 3D printed objects in your daily life that you might not even know about. And I see that number increasing, here in the near future. So looking to kind of get into more practical applications in our everyday life for 3D printing, 3D printing furniture, 3D printing, again, just daily things that we could be using in our homes that could otherwise, we could have a printer and print it on demand, not having to pay for shipping, not having to wait, long lead times for different parts. Also wanted to highlight, almost forgot, I had a part that failed on my garage door last week. It was a gear that was up in the motor box. And I designed the gear, reverse engineered the gear. My 3D printing technician, Spencer, and I worked on this design and printed it in about 3 hours with a 0.6 nozzle on the Ultimaker 2 Plus Connect, out of a TPU that was Armadillo from Ninja Tech, and really, really robust stuff. Armadillo is crazy strong. I think it's in the D shore range. Don't quote me on that. I think it was in the D shore range. So really more like a rubber than kind of a more flexible TPU. But a lot of different daily applications that I couldn't otherwise find this garage gear on the company's website. So I redesigned it and printed myself one, and it's working perfectly fine now in my house. So a lot of different applications. If you have any questions about things that you're looking to try to design and print, we'd love to work through that with you here at Ascent Fab. Hopefully this was a little bit more helpful in kind of starting to get your mind to think about, how I want to use 3D printing either in my clinical practice in prosthetics and orthotics, or elsewhere outside of that. Think about those design criteria that you're looking for and really utilize those techniques to focus in on how best to print your part. So thanks very much for listening into this week's episode of Fabrication Friday. Tune in next week for some more fun. All right, thanks.